Okay. Just a heads up, I need to go a little bit earlier today for an online conference starting at 2. So maybe roughly like 1:45, 1:50. This is what we have from last time, the Euler's method. Okay, it's exactly the same as one dimension if you write everything in terms of vector notation. But if you write everything out, yeah, it's just what we have here. Okay. So it's pretty straightforward. Knowing R0, you want to find R1. Knowing R1, you want to find R2, and just keep going until you find all the R, one after another. Of course, it's just an approximation. It's not the same as the correct one. But if you let the points to be a lot, which means smaller h, then find the difference give you more and more accurate derivatives. Then eventually this one will converge to the real one. Okay. So now to just give you one quick example, this is what we do for the predator and the prey. We set up some parameters, alpha, beta, gamma, whatever. And then we start with some initial calculation of rabbit with 2 and fox with 1. We want to consider the differential equation systems. On the interval from 0 to 10, you pick the units, maybe 10 years. Okay, you want to figure out what will happen during the 10 years on the year 1, year 2, year 3, and year 5. So basically, we take 100 points for approximation, just for illustrations. If it's not good enough, do 1,000 points. If it's not good enough, 10,000 points, and so on. But once we have that, first, we have 0 to 10. That's a total length of 10, divided by 100. That means for every single step size, we should take 0.1. So 1, 2, 3, 4, 5, 0.1, 0.2, all the way you have after 100 ones, you got 10. Okay. Now we do know R0, which is just R at 0, which is 2. F0, which is F at 0, which is just 1. That's where we start for the first term. Now we want to compute R1, which is basically the value, approximate value at 0.1. Technically, you should put a hat here. That's not the real R. That's the approximation of R. And F1 is going to be R F hat at 0.1. And then R2, R hat 0.2 until R 100. Then you know it's going to be R at 10. So up to there, you know all the points, okay, from the first one to the last one. Okay. And the iteration looks exactly the same as what we just did here, except you change X and Y to be R and F. So let's just do a very simple first iteration. R1, F1 equals R0, F0 plus delta T. In this case, it's 0.1. Okay, which come from 100, 10 divided by 100. Okay, times Ftn, which is basically Ft0, R0, F0. What is your F? Your F is just the first equation. Okay, so 2R0 minus 0.2 R0 F0 minus R. What did I do? I should use I here, F here. Okay, minus F0 plus 1.2 R0 F0. And you do know all the values of R0 and I0. So 2, 1 plus 0.1, 2 times 2, 4. Yeah, let's just put it in. Four minus 0.4 is 3.6. Minus 1 plus 1 times 2, that's 2. No, 1.2. 2.4, so that's going to be 1.4. Together, it's going to be 2.36, 1.14. That is going to be R1, F1. That's going to be what happens if we use the approximation using the differential equation, starting from 2.1 and after 0.1 years. This is our approximation. Sounds good. What about R2? You just repeat this thing here. Whenever you see a R0, replace it by R1. Whenever you see F0, replace it by F1. So knowing all the information at 1, you will be able to find R2. Then put all the information you just found for R2, you will find R3. Keep going, keep going, keep going. A for loop will do everything for you. So if you have checked the code from 1.5 or 6 of Euler's method, this one is just exactly the same with the vectored format. Sounds good? Okay. All the idea, of course, come from the key part, that is yn plus 1 minus yn over h is almost y prime. Okay, then y prime is nothing but your f tn yn. That's how you actually got everything here, which give you yn plus 1 equals yn plus h, which is your delta t. Let's use delta t instead. Okay, ftn yn. What really you have here, even though I write it down in this way, is actually y prime. Okay, so that's how we use the information from the differential equation. All right. Everything makes sense there? Any questions? No, let's code it. Okay. Chrome, okay. Do you guys see my screen? All right, so now what we have is number 1, the first Euler's method. That's what I put here. Okay, basically what you do is you just replace the derivative to be xn plus 1 minus xn divided by delta t, and then do the algebra. Suddenly you have this. That means knowing what happens with 0, you can find 1. What happens with 1, you can find 2. Okay, and keep going. Then we tried it with the predator and prey model, which we have done before. And now we just need to do it for 10 points with the for loop. That's what we got. Okay. Of course, it's wrong. And it's probably because we took too few points. We only have 10 points. How about we do 100? Good enough? At least it should show some pattern, right? This is what you get for 100. Even worse. Okay. What about 1,000? Okay, keep in mind you're basically timing 10 every single time. That's a lot of more resource than before. Well, now everything starts to make sense. Sounds good? So number 1, if you remember the Euler's method we did for 1 dimension before, we do not need too many steps, but however, too many points. However, for this example, when we have 2 things involved, the arrow actually accumulates at least doubled because you have 2 things. Each one has an arrow, and each one is going to give the next step additional arrows. So you require much, much, much smaller time steps. That's the first observation. Good. Question 2. Do you think 1,000 is good enough? Well, take a look. What do you have? A periodic behavior, right? Second, every time you move forward for one more period, it seems like the amplitude become bigger. It starts with 4, but if you do it with 20 years, the fourth cycle actually give you a 5 in total. Sounds good? Now, let's just require even more resource. When you try with 10,000 points, what do you see? The pattern we just saw is gone. Right? Now you don't have to increase the amplitude, or maybe you do, but it's not so dramatic. It's not from 4 to 5. Maybe it's from 4 to 4.01 or something like that. Still okay? So 10,000 is probably the place where we start to see the solution make sense. But then the question becomes, is 10,000 good enough? Are you sure that if you do 100,000, the thing won't become like a damped periodic function? Are you sure? Do you see the problem with Euler's method? Okay, how much is enough? I feel like 1,000 is good enough for 20. In an interval of 20, it turns out, no, it's not. 10,000 is better. We can't say it's enough, right? So what do? You try even more. Maybe 100,000. Okay. Well, maybe there's no difference than 10,000. Maybe it's just too small for your eyes to see. Sounds good? Okay, so that's a big drawback of Euler's method. Actually, if you just do something which you think is enough, for example, 1,000 point, which give you some meaningful graph, you should be happy. Every time you see something like this, you should be happy. And then you tend to think, wow, will be the real behavior of the thing. Because Euler's method is awesome, and this one clearly makes sense. Turns out you have a lot of mistakes to make if you just trust this graph here. Okay, so that's the problem. Another example is more easily to see because you have harmonic oscillators. You know the answer is going to be a sine, cosine. You're going to have a periodic function, right? And amplitude has to stay the same. But now if we think about it, we just do it with 100 points. This is what you get from Euler's method for that system. It tells you the spring stays steady until, where's it, 100? Yeah, until the 82nd, that thing starts to shake a little bit, which doesn't seem right. So you suspect it, you change it to be 20,000. 20, not here, 20,000, 1,000. Is it right? Not really, because you know ahead of time the amplitude should not be this. What about 10,000? Can you see that thing still shake? And the amplitude become bigger and bigger and bigger and bigger? For this particular problem, which is not hard, by the way. Now it's more like it. Okay, again, is this good enough? 100,000? I have a pretty decent computer. You can see when I push to 100,000 with only 2 variables, that thing start to lag for 1 or 2 seconds, right? Do 1 more 0. How much longer do you think it's going to take? And I would rather to stop here. I have no idea how long that thing is going to take. Oh, we got arrow, so that's a good thing. It's running. Okay. Well, all right. And we only have 2 species. What if we have 3 or 5 in real life? Okay. That's everything we have for numerical method. From here, hopefully I show you something that is for the Euler is great because it's easy. Meanwhile, it sucks because it's really not accurate. Plus, you don't have even a single idea when you should stop. How much do you wish that, number one, you should analyze the system before you run the numerical method so you know the solution roughly should look like something with constant amplitude. That's one way to figure out what's wrong. A second thing is how great it is that if the algorithm itself will be stable, it will not be less prone to how big the h is. Especially Hopefully that thing doesn't break like this, because I may trust it. This looks so nice. Okay. That's roughly the idea of Euler's method. Up to now, we start to see Euler's method is a little bit, how to say, limited in terms of stability. Now, how do we modify it? Well, number one, of course, I can give you something advanced, which basically is a whole new method, which is more complicated. Of course, that's supposed to be better. Great. But now we just want to do a little trick to change the Euler's method, to change it from explicit to implicit. And I want to show you, even by just changing how you construct it, which means it's roughly the same complexity, not way longer or way more complicated, but somehow you achieve something called stability. Again, just ideas, not the careful proof. Let's think about this differential equation, or even just 0.1y. Y0 is 200 or something. Okay. Now let's talk about forward or explicit Euler. Okay, which is basically what we had before. Delta t times 0.1y. Where does it come from? It comes from here. Sounds good? Now let's talk about something called backward Euler method. Which come from the same thing. Actually, if it's the same, why don't I just copy it? Okay. But we do one more tweak. That is, instead of doing Tn, I change this to be Tn plus 1. What are you trying to do? You have some curve. You have Tn. You have Tn plus 1. Okay. You have a second line. Before, you were trying to use the second line to approximate the derivative here. Now I'm just saying, like, how about you just use it to approximate the derivative here instead? You know, when h goes to 0, these two will be the same, right? One is the left end point. One is the right end point. So if your interval is really small, they should be very close to each other. So it really doesn't matter which one you use. Theoretically. Sounds good? All right. Now, this is basically, again, Euler's method, but this one is called backward or implicit. Why? The reason is the following. Before, it was explicit because you know how to get n plus 1 directly from all the information from n. So yn plus 1 is on the left. Everything with n is on the right. Sounds good? For the new one, what's the difference? It's roughly n plus 1 is here and n plus 1 is here. So if you want to go ahead and do it, you have to solve the equation implicitly to get yn plus 1. You actually need to solve an equation. Solve for yn plus 1. For the case we just did, we do a simple calculation. Before we have 0.1 yn. That's explicit. If you know yn, you can find yn plus 1. But this time, let's change this to n plus 1. Then if you time everything on the other side, just as before, okay, yn plus 1 equals yn plus delta t 0.1 y. If it's n, it's explicit. Knowing y0, you can find y1, but now it's yn plus 1. Which means you're not done unless you go ahead and try to solve now it becomes explicit, but that is after you solve everything for yn plus 1. That's basically the difference. Okay. That's the explicit. To make it more precisely, it's 1 plus delta t 0.01 times yn. Okay. Now we have the implicit. Forward, Euler. Backward, implicit. This is explicit. This is explicit. If we write both here, that'll be what you get. Is everything clear how we derive the backward Euler? Okay, we just change a small thing. For this case, it's actually easy because it's a linear function of yn, so you can move yn. If there's a yn square or something in the f, it becomes more complicated. You have to solve it. Okay. Do you recall the comment I made at the beginning? The implicit one is more stable compared to the explicit one. That means 2 is better than 1. Actually, don't say better, stabler or more stable than 1. Judging by the scheme, can you see why? Okay. Basically, what you have is yn plus 1 equals yn times some number, right? Okay. What's the number here? What's the number here? Okay. So basically, you will have a geometric sequence, sequence. Okay. Then which one is stabler totally depends on which one is more likely to go to infinity sooner than the other one. Or it's the same as which one has a bigger ratio. So it becomes a matter of which one is bigger. More precisely, these are the same term. So let's just say 1 minus a and 1 plus a. Okay, where a equals this. Which one is bigger? Am I doing the right thing? 1 minus this, yeah. That's why I want this. So in this way, I cannot say it's better. So there's no shortcut. Okay, this is bigger than that. Therefore, this is bigger than that. Therefore, this is bigger than that. So this one has a bigger ratio. That's not ideal. So probably I have to go through the whole proof. I was thinking this was easy to show. Turns out it's not easy. How much time do I have? 40. Well, since it's already not covered in the book, I would just say, I just did a quick thought. I thought this will work, but this will not show directly. I was doing the wrong direction. Okay. But what I can recommend you to do is that I have to rely on yourself. I don't have time to go over it then. The true proof will involve, okay, to use the fact this one equals which is from calculus 2. I was trying to skip this. Turns out I cannot skip it. Okay. So try by yourself. Then it's almost like I'm giving you the complete proof. So at first I said this is intuitive. Now I need to say it's not intuitive. You have to go through the proof. Sorry about that. Okay. I was thinking it was pretty easy to show. No. Okay. Either way, backward, Euler is more stable than the forward Euler. Not more accurate though. It's just harder to break down. Because they are both first order Euler's method, their accuracy are very similar to each other. Okay. I didn't do it. You can try to code it yourself. The key here is for the predator and the prey, or the harmonic oscillator, either way. We roughly achieve a reasonable result with 1,000 steps. Okay, 10,000 steps for the interval from 0 to 10, 0 to 20, roughly. Okay. Use this setup. Try both explicit and implicit. Your expected result is implicit should give you something reasonable at 1,000 steps. You don't have to actually go to 10,000. The code is already posted online, so you can actually go there and try to modify it to somehow do a for loop to figure out this fact. Sounds good? All right. I think that will be all for today. I can stay for 5 more minutes if you have questions. So I will do that.